So we are AngelStrike. So I am Kyle Hallam. I don't know if we want to introduce everyone.
You can if you want this one.
Okay. How do you want to do that?
Just have them kind of do like a
Should I
script.
turn this or?
No, just have them just go around.
All right. Go ahead.
All right. I'm Mustafa Yusuf.
I'm Nate Hyde.
I'm Luke Schiefelbein.
I'm Eric Joyce.
I'm Christopher Winnie.
I'm JJ Hu.
I'm Anthony Kumba.
I'm Zach Swanson.
I'm Eric Middleton. I'm the team leader.
And our project advisor is Matt Nelson. So basically this project objective is to build a fully autonomous hexcopter UAV, and it should be flying in a GPS denied environment. This limits us, well, I'll let somebody else talk about the competition rules. So our short-term goal is by the end of the semester we should have our body manufactured, our sensor libraries written, and we should also have electronics mounted, so we should be ready for testing. Also, I will be talking about this later, but I plan to do FEA modeling. So long-term goal is to compete in the AngelStrike competition, the AUVSI International Aerial Robotics Competition, and that's held, I believe, in Arkansas currently. So about the competition.
Well, I'm going to talk about the competition, which is hosted by Association for Unmanaged Vehicle System International. The purpose of this competition is to move area robotic forward to perform a mission, a useful mission, or a challenge. All right, and the mission right now deemed impossible. This time proposal. Well, the concept is to interact between the aerial robots and the ground robots. We should navigate without navigation aids and interact between multiple aerial robots. Well, the current challenge is Mission 7, which is crawling 10 ground robots through this aerial robot we're making. And then the ground robots are randomized and autonomous. And it can be controlled by rare earth magnetic. We should be avoiding three ground robots which has a cylinder top above it, and that's it. And the general design we'll talk about.
All right, so for the general design, we decided that our hexcopter would be the most beneficial. So we got our 6 rotors, and then on the bottom we're going to have the sensors going down for vision, and then we'll also have 2 cameras at a 45-degree angle to help with our depth, and they'll get more into that in electronics. But yeah, and then on the top, then we'll have our XB and communicating with the base station, which will also be talked about with the electronics group. Okay, so for underneath the hexcopter, we're going to have the body, then we'll have 2 platforms with the sandwich with the battery between. Then we'll have the optical flow facing down with the sonar. That'll help with our height to make sure we know where we're at. And then we'll have our infrareds mounted underneath facing out so that we can, for object avoidance with the other, I guess not hexcopters, but other aerial vehicles, make sure we're not hitting anything. And then this is our body. We're gonna pretty much using the same concept as our hexcopter design, except for that we're remodeling, for our quadcopter design, but remodeling for our hexcopter. It's gonna be a piece of foam. It's sandwiched between 2 pieces of carbon fiber. And then we will be using aluminum brackets to accommodate the battery and different mounting for the electronics.
Right. So now about the top of the hexcopter. What we've got on top of it is going to be these 6 motors on each of the ends, on the ends of the arms with the propellers, and then controlling each of these motors, we're going to have 6 ESCs
ESCs at the beginning of the arms, equally spaced around the hexcopter. And then in the middle, we've got the electronics to communicate with the base station and some other processing electronics there, the RDcopter XB and the video transmitter receiver. Now about the semester progress so far, at the moment we're ready to start the carbon fiber layup. We have our piece of foam ready to be used for that. We've got it all cut out and everything. And then we have also completed some temporary landing gear that we've made out of blue foam right now. And those are ready to be put onto the hexcopter, although we plan to make it probably out of 3D printed polymers when we do make it for the final design. And I'll let Kyle talk a little more about the progress.
So semester progress continued as far as structures. We're currently working on a vibrational analysis model in Abacus. And basically that's just your forced vibration modeling. So there's not a whole lot to it. We're just having a learning curve at the moment, learning the finite analysis modeling structure. Now onto the electronics. These are the sensors that we'll be using on the hexcopter to keep it from crashing into anything and make sure we can herd the robots, know where they are at all times. So to start, we're going to have an ultrasonic rangefinder. This will be used to point it directly at the bottom of the hexcopter to measure our altitude. Then we're going to have 4 infrared proximity sensors. These will be pointed outwards to give us 360-degree coverage of anything around us, or obstacles that are coming near us, or anything that's around us. Next, we have the ArduPilot sensors. We have the inertial measurement unit, and that includes the accelerometer, barometer, magnetometer, and also a gyroscope. And all those just make sure that the hexcopter doesn't fall out of the sky. And lastly, we have the electromagnet, and that will be used to manipulate these ground robots. And now a little more about how we're going to communicate with the base station and with the ArduPilot. All of our sensors will be sending their data to an Arduino Mini, and the Arduino Mini will send that data to the base station using XB, transmitter and receivers. Then the base station will process the data we get and send the decisions back over to the Arduino, and then send that data onto the ArduPilot, which will then move the hexcopter. And the only thing that will not follow this little diagram drawn out will be the cameras. And the cameras will have their own transmitters and capture cards that will send directly to the base station.
Okay, so for the motors and ESCs, we'll be using a Rimfire 400 and an RC Proton 40 amp. We chose these devices. One, the motors have a good weight to thrust ratio, and the ESC and motors also include a good bit of safety features. For example, the motors have double bearing shielded, just in case they get hit by something, it won't bust. And the ESCs include safety features for if there's a fire, the ESC will stop sending ampage. We also chose the ESC because of the continuous 40 amps given, and if we need be, we can send 60 amps to the motors for max acceleration for collision avoidance. For guidance, we'll be using an ArduPilot. Listed below are some of the features that are given. We'll actually be using a 4DR APM ArduPilot with an open source called ArduCopter, which will be used to keep the aircraft stable and give us data points. In the beginning of the early test stages, whenever we get available fly space, we will use the GPS to test out our aircraft. With the data from the ArduPilot, we will send this data to an Ardu Mini. The Ardu Mini is located on the aircraft. It will gather sensor data and data from the ArduPilot, collect the data, put it in data packages, and then send it to the base station. And the base station will analyze the data and then send it back to the Ardu Mini.
I'll be giving an overview of libraries. First of all, the definition of a library. For programming, library is a collection of a resource and objects, including some pre-written codes, some subroutines, templates, classes. And the reason that we want to use libraries is because that library provides some very useful resources for software or program developments. And the standard libraries usually include some very core fundamental functions, including even a mechanism of input or output. And as our team member just mentioned, our Hexcopter equipped with a Arduino Mini on board. Arduino actually provides a variety of libraries, including servo library, including sensor libraries. But we decided to go with our own library, create our own libraries, write our own code. There are reasons for us to write our own library. The main reason is to make sure the code that we wrote will work well with each other. If we download it from here and there, they may not really cooperate well with each other. And also, since our project is a competition oriented project, we would like to keep our project, our code and our project, the originality of it. And last but not least, writing our own code will help us to maintain the structure of the code very organized and just also benefits the future use.
All right, so I'll be going over the libraries we are just working on right now. First, trying to kind of go with each other. I'll go with the task queue. The task queue holds all the processes we're going to do, have them in a list so we can execute them one by one in order. The scheduler schedules them and orders them. We can add tasks to the task queue or take them away. And we also execute them through the scheduler. Next library is the infrared library, is the one I have actually been working on. And this will take in the readings from the infrared sensors we have and converts the voltages into meters. And we actually have a picture right there. The get and reads in the signal from the pins, and we use a formula to change it to centimeters. Then we change that centimeters into meters. And there's also an accuracy for the sensors, which is from 10 centimeters to 80 centimeters. Otherwise, it'll just output 0 for right now. Next is the ranger, which is similar to the infrared, which will convert the data we get from the motion and change it into meters. So it's the same thing like the infrared. And the base will communicate with the base station, and it'll retrieve and send data from it, and also check, see if the data coming in is viable and not corrupt.
So the base station, which is processing all of our data and information, will need to be fairly powerful. So we're using one of the M2I provided laptops with the specs on the screen. And all of the programming for the base station is done in C++, and we're using Visual Studio. And we are also using OpenCV libraries to process all the visual feed from the cameras.
All right, I'm going to talk a little bit about the software we're writing for the base station. First and foremost, it has to process 3 different video feeds. As they mentioned earlier, we have a stereo pair of cameras that are facing forward and 45 degrees down. We also have a camera facing directly down, which we are doing optical flow with, as well as other analysis. We have to perform localization with those video feeds. The arena is marked with certain colors of tape. So we need to gather information about where those are at and turn that into a location for our Hexcopter. We also have to identify the ground robots. The only way we can identify them is based on shape and probably color. They're all white. So we have to analyze all 3 video feeds to figure out where they're at, and then keep an update as to where we think the ones we can't see are currently at. We also have to do decision making. We have to figure out which robots are in the greatest danger of leaving the environment. And then once we figure out which one we need to go for first, we have to figure out the best way to manipulate that target while still monitoring the rest of them. We have two different ways we can actually alter the ground robots. The main one we talked about earlier is to use some sort of a magnet. Ours is an electromagnet. So if we get extremely close to the ground robot and pulse the electromagnet, it will turn 45 degrees clockwise. So if we want to turn it 180 degrees around, we have to pulse the electromagnet 4 times. Otherwise, we can land directly in front of the robot. It will detect that it hit something and will turn 180 degrees on its own. So we have to decide which of those is the best option and then go from there. And then finally, we take all this information and all the decision making we did and send them as commands to the UAV. That'll be going to the Arduino Mini, which will then convert that to a format that the RG pilot will accept, and it will then fly accordingly. With that, I'll open up the floor for questions.
Oh.